there, folks. Back here with another video where we are, like I said in the last video, kind of making a transition in topics. We are moving from our study of the derivative, which we noted for quite a few lessons now, is some application of a limit and is used to find slopes of lines tangent to curves, and is used to explore instantaneous rate of change in a function, right, to a topic that is somewhat related to the derivative, in the sense that what we're going to be looking at is going to be an inverse operation to differentiation. All right. An inverse operation being an operation that undoes differentiation. All right. If we kind of think about the two being applied successively, right? Applying a derivative and then applying an antiderivative, they would undo each other, or vice versa. And like I said, that's where we're heading, is we're heading into, as I had just noted there, the study of what we call antiderivatives. All right. And what we will see is that this antiderivative in our study is going to be related to a topic known as net area. It's going to help give us and help us calculate area trapped within a curve region, right? A region bounded by a curve. And it's going to be another example of application of limits. We're going to also see that connection here in our study of calculus to the idea that calculus is the study of limits. All right. Again, though, what we are looking at is the antiderivative. It is right here on the cusp of discussing this topic of net area and leading this into what we would describe as the topic of integration. All right, that is where we're heading here, folks. But let me bring up the notes. Here's our notes for this lesson. We're going to talk a little bit about what's called the antiderivative, right? And as I had noted here, the antiderivative of a function is an inverse operation to differentiation. All right. In other words, the antiderivative of a function little f, right? If we think about the antiderivative of a function little f, it is going to be what we call this function capital F. All right. Such that what's true about the relationship between these two functions is that they are related to each other, but although not identical, so that's why they do have two different names. This is little f, or lowercase f, and this is cap F, or capital F, right? Where there is the relationship to each other in the idea that they are both related to each other through the idea of using the name of F, but they are different in the fact that this one is called cap F and this one is not, right? And how they do relate in terms of behavior is that cap F's first derivative is equal to little f of x. All right? When we think about the antiderivative of little f being cap f, right? What's true is cap f's first derivative is equal to the function we know as little f of x. Right? And we see that develop in the following definition here. This is what the idea, the relationship that the following definition presents, and also presents a little bit of notation for us, right, in this definition. So let's bring this up. Here's our definition of the antiderivative of little f. And for a function y equals f of x, right, the antiderivative of little f, denoted as this, right? Let's put a comma in there, right? This is a little just side note here. Is denoted as this. This is known as the antiderivative notation. What we have here inside the brackets is function f of x. And what we're applying to function f of x is the antiderivative operator. The antiderivative operator being this integral, or this is going to become known as the integral symbol, the antiderivative symbol here, that is happening with respect to variable x. This dx is highlighting here at the end the variable of interest in our integration. And what we're doing is we're taking function, see if I can say it this way, f of x, right? And we're applying to it that integral operator with respect to x. And what it equals is this result here. Right? This result, cap f of x plus c, right? Where cap f of x plus c, we saw this also discussed in our previous lesson with mean value theorem, is a family of solutions, right? Is a family of functions representing a family of solutions for the antiderivative of our function little f, all that differ by simply a constant value. The antiderivative of a function is actually a family of solutions, a family of functions, all related to each other, looking very similar to cap f, except they differ by a constant value. And what's unique about cap f, as we had noted, cap f's first derivative is equal to little f of x. Right? That is how we define the antiderivative of a function. Let me give you some example here. We might consider the antiderivative of f of x equal to x squared. Right? The antiderivative of f of x equal to x squared would be given by the notation given by applying the antiderivative operator to function f of x, which for function f of x equal to x squared would look like this notation seen here, where if we spend just a moment thinking about what that result would be, that result, through the definition, would be equivalent to 1/3 of x cubed. 1/3 of x cubed plus some constant value of little c. Right? And the reason we could say that it is equal to this family of functions that are all a small transformation, a vertical compression of the cube function, right, x cubed, is because if we take the derivative of 1/3 x cubed, if we apply the derivative operator to that argument, the derivative operator applied to that argument would yield x squared, the argument given by our initial function f of x. All right. As we go on to note, this is the antiderivative of little f of x equal to x squared, since if you take f of x's, cap f's equal to 1/3 x cubed, first derivative, all right, let me make that adjustment there. Again, that's why I'm going through these with you folks, as I am trying to also kind of proofread these with you. All right, this gives us 1/3 x cubed, where if we apply our rules of derivatives, bringing that power 3 out in front, it will cancel out as a constant multiple with the value 1/3 and reduce its power by 1, dropping it to the value of squared. So we would end up with 1 times x squared, the 3 canceling with the 1/3, yielding the 1 out in front, times the quantity given by x squared, where we reduce our power by 1. Right? That would be known as the antiderivative of the function f of x equal to x squared. Its antiderivative is the family of functions 1/3 x cubed plus c. Again, because if you take the derivative of 1/3 x cubed, it yields this argument x squared. All right? Fundamentally, with a few basic cases for functions, we can reason the logic for what would have to be the antiderivative given by cap f, right, for our our calculation. However, like we did in this case, right? We really just did a little bit of quick thought. We think about, well, what's going to cause a function to have an antiderivative of x squared? Well, that's going to be a cube function. But I just can't take the derivative of the cube function, because if I take the derivative of the cube function, that's actually going to leave me with 3x squared. So in order to reduce that 3 by 1, what I do is I end up multiplying by a third. And that 1/3 will cancel with the 3, which will leave behind the value of 1 times x squared. But that 1/3 would have to then work itself into the constant multiple of the cube function, x cubed, where we're applying the derivative operator. Right? I can logically think out what it would be the antiderivative in the case for this rather basic function, the square function. As we grow in complexity, as that function goes from the square function to a quadratic to any polynomial function, things are going to get a little trickier. So there are going to be rules here, folks. All we're doing initially here is establishing an understanding of the definition. All right, but we are going to see some rules developed by the end of this note set. All right, let's logically think through another example here. Or we could consider the case for the antiderivative of f of x equals the cosine of 2x. Right? The antiderivative of the cosine of 2x, right, would be given by the notation of applying the antiderivative operator to function f of x. In this case, f of x is the function cosine of 2x. Where I know that the cosine of 2x, it develops from having the derivative for the sine of 2x. All right? If I take the derivative of sine of 2x, that's going to lead me back to a cosine of 2x. However, it's not going to yield just the cosine of 2x. It'll also yield 2 times the cosine of 2x. So I need to incorporate a 1/2 to cancel with that value of 2 when I undo the antiderivative's value. Notice when I apply the derivative operator to 1/2 sine 2x, it will yield the cosine of 2x. Right? And that's how I know it is the antiderivative of the cosine of 2x. All right? When I apply the derivative operator to 1/2 sine 2x, it does yield the cosine 2x. All right? Again, I logically think that out. To begin with, I can say, well, I know that the derivative of a sine of x will yield me a cosine of x. So that kind of gets me going, where then I can note, well, how do I get the interior to become 2x? Well, the interior, the independent value of the sine function needs to be replaced with the argument 2x. However, when I take the derivative of the sine of 2x, I understand the result there is actually going to reduce, or the derivative result is going to produce 2 cosine 2x. Where how do I eliminate this 2 out in front as a constant multiple? Well, I would have to multiply it all by the value of 1/2. And the 1/2 will cancel with the value of 2, leaving behind just the value of 1. 1 times the cosine of 2x being cosine 2x. Well, to make that a constant multiple of 1/2 out in front, to multiply by that 2, I would need to have the derivative with respect to x for 1/2 sine of 2x. There is a bit of the logic. All right. Now, there are going to be other rules that develop. The logic on these get a little heavier the more complex the function becomes. These were two rather simple cases here. Rather basic cases. As we see more complex scenarios, the rules are going to get a little bit more complex. All right? And we're actually going to develop rules that are going to help us with the calculation. The logic is going to get a little bit more complex, where we're going to benefit from the use of some rules. And in fact, that's what we start to set up here, right? In general, there's a list of fundamental rules. The list is somewhat limited. As we see here, there's going to be about, 14 rules in this set. But this is where a majority of our foundations for antiderivative calculations will develop from this set of 14 rules. All right? And they're presented in the following theorems. All right? The first theorem that we see is known as the sum and difference rule for antiderivatives. Right? The rule, right, essentially tells us, if we were to think about it in other words, is that the derivative operator, when applied to the sum or difference of two functions, right? If we take the sum and or difference of two functions here, and we apply that antiderivative operator to that argument, that antiderivative operator will distribute itself across that sum and difference, sum or difference, all right, yielding the individual sum or difference, right, for the antiderivatives of our functions f of x and g of x. Where, when we think about how those would sum together, right, it would be a sum or difference of their individual functions, antiderivatives, cap f and cap g of x. All right. The antiderivative operator behaves very intuitively, very similarly to the derivative operator with regards to a sum and or difference. Right? It distributes itself across that sum or difference without hesitation. Right? It's a rather intuitive result. If we do a little proof, here we might assume h of x is the sum or difference, cap h is the sum or difference of two antiderivative functions, cap f and cap g, where when you take the derivatives of cap f and cap g, you get little f and little g. All right? And when we think about the derivative of h prime, or cap h prime of x, it is going to be equal to, and we probably should note that in here, the derivative with respect to x for cap h of x, which is going to be the derivative with respect to x for f of x plus or minus g of x, right? Which in yield is going to yield from our derivative rules f prime of x plus or minus g prime of x, which is equivalent to little h of x, right? In our understanding of the antiderivative operation from the definition of antiderivatives, or derivatives, we should say. The same, right? The definition of the antiderivative and how it relates to the derivatives. All right? So from the definition of the antiderivative, when we think about cap h of x plus c, it will be equal to the antiderivative operator being applied to little h of x. And if we apply the antiderivative operator to little h of x, it's going to be like applying the antiderivative operator to cap f's first derivative plus or minus cap g's first derivative. As we had noted, those values, their derivatives, are equivalent to little h of x. So, in turn, since those first derivatives are individually equal to f and g, little f and little g, we end up with the antiderivative of little f of x plus or minus little g of x, yielding, well, being equivalent to cap h of x plus c. And since cap h of x plus c is equivalent to the sum or difference of little f, or cap f plus or minus cap g, as we had initially assumed, right, which led to these conditions here, right? We can then say that that antiderivative for little f of x plus or minus little g of x, which is equal to cap h of x plus c, must be also equal to cap h of x, cap f of x plus or minus cap g of x plus c, right? Where what we're illustrating here is this antiderivative operator distributing it itself across the sum or difference to the individual functions f or g, right? Proof of the above result. Now, before I give you an example, where we are going to see this used is in finding the antiderivative of polynomials, very similar to how we did for derivatives. So, in order to get to finding the antiderivatives of a polynomial function, there's a few other rules I need to present you with. So the next rule on our list that I want to show you here is going to be the constant multiple rules of antiderivatives. All right, so if we look at the constant multiple rule, folks, it plays out very similarly, very intuitively, like the constant multiple rule would for differentiation. If we think about applying the antiderivative operator to some constant multiple times some function, that constant multiple can be factored out of that antiderivative operation. Very much like what we see happen in differentiation. All right. Here, the end result for the antiderivative of n times f of x is n times the value of cap f, where cap f is again the antiderivative, the antiderivative of little f. Its derivative is little f of x. All right. If we look at a bit of proof, we might assume f of x is the antiderivative of little f, and that does imply that the first derivative of cap f is equal to little f. And it is known for any number n that n times f prime of x would be equal to then n times little f of x if these two quantities are equal to each other, implying n times f prime of x must be the antiderivative of n times little f of x, or when you apply the antiderivative operator to n times little f of x, right, this is equal to n times cap f plus that constant value of c. Right? Again, here a rather direct proof, right? Following rather directly from the idea that n times f prime of x is the antiderivative of n times f of x. That is, that if I take and apply the derivative operator to this quantity, right, if I think about that, I might say this is implying that if I apply the derivative operator to n, well, let me say it this way. To n times the derivative of cap f of x, this is like finding n times little f of x. Right? Because we know this derivative operator, how I might go ahead and write this. Can be written as this constant multiple seen here. Oh, got to remove this dot. All right. So, from the intuitive result that we see back in differentiation, we can use that to draw conclusion for this result that we see in integration, all right, or in the antiderivative operation. All right. Again, we're not going to see any examples of this yet until I show you this last theorem, which is going to give us all the techniques we have for being able to find the antiderivatives of any polynomial function. All right. This third rule is called the power rule of antiderivatives, and it starts off by just saying let n be any real number, except n can't be -1, and we're going to see why here in a moment, right? The antiderivative of x raised to the power of n, right? It's going to be equal to x raised to the power of n plus 1 divided by n plus 1, plus the value of c, c being, again, any constant. Right? It is the power rule for antiderivatives. It tells us how to find the antiderivative for the power of some function of x, or of the function x itself. That power, n, increases by 1 to become n plus 1, and then we divide by that new power. We divide by n plus 1. Right? Similarly, if k is any constant, we let k be any constant. If we apply the antiderivative operator to that constant, it will be applying that antiderivative operator to the constant times x to the 0 power, because we understand x to the 0 power is equivalent to 1. Right? So instead of writing it as 1, we write it as x to the 0 power, and here we can apply the constant multiple rule, and I probably should say that here, where we can factor out that constant multiple k and say it's k times this antiderivative operation, where the antiderivative of x to the 0 power, right? Let me write that like this. So we had noted that is going to be x raised to the 0 plus 1 power divided by 0 plus 1, right? Which in turn is going to equal k times x to the first power, right? Which is just k times x plus the value given by the constant of c. Now, constant k times constant c is just another constant c, right? And we could draw this result out here. Right? Let me break this up slightly. Let me take this part of the argument and move that down below here. Ends up equaling this down here. We'll just save a little vertical space in that theorem by arranging them linearly, right? These equalities linearly, right? But this is the derivative rule for a constant. Basically, the derivative of a constant is the constant times x plus c, if we're finding the antiderivative with respect to variable x. Right? And that is because that variable x is being raised to the 0 power. Now, we do note there is one exception for a power up here, and that is that x can't be raised to the negative first power. And the reason would be is that, first of all, you'll notice if I plug in -1 here, I'll have -1 plus 1. This will result in 0. I'll have x to the 0 power up top, which will turn into 1. But I'm going to have to divide by -1 plus 1. And dividing by -1 plus 1 is dividing by 0, and the whole value becomes undefined. So this power rule does not work for the case when n is equal to -1. It works for every other power, including the power of 0. Right? Where we can use that in the case for finding the antiderivative of a constant. Now, these three theorems here above can be used to find the derivative for any polynomial, and we will see that. Now, I do want to give you a proof of this theorem. I'll quickly give you a note here. Letting f of x equal this derivative, x to the n plus 1 power, we can see that if we take the antiderivative of f prime of x, that would be the derivative with respect to x for x to the n plus 1 power divided by n plus 1, which is going to result in n plus 1, right? This power of n decreasing by 1, while we bring that power of n plus 1 out in front as a constant multiple. Now, if we do that, this n plus 1 minus 1 is going to simplify to the value of n, and the n plus 1 divided by the n plus 1 is going to simplify to the value of 1. And this is all equal to x to the nth power. So let me put on a conclusion here. So the integral of x raised to the nth power, all integrated with respect to x, must equal x raised to the n plus 1 power, all divided by the quantity n plus 1 plus c, since for little f of x equal to x raised, oh, be careful there, since I'll say here, for big F of x equal to that result of the power rule, x raised to the n plus 1 power divided by n plus 1, the derivative with respect to x for cap f of x, which equals the derivative with respect to x for what we just said here, let's say it this way, f prime of x equals x raised to the nth power, right? And I think that would probably be a better conclusion to the proof, right? Make full statement, right? Make that connection. Now, as noted, we can use these three theorems to find the derivative for any polynomial function. So we might consider finding the antiderivative for the polynomial function f of x equals 5x squared plus 4x minus 2. Right? Its antiderivative is given by this argument seen here, right, in notation, where if we get into calculation using the theorems above, the first thing we would do is distribute that antiderivative operator across this sum and across this difference, and it would distribute to each of those terms. Now, once distributed to each of those terms, in each of these terms we do have a constant multiple, and this last term has an argument that is just a constant. So we can use the rules above. Well, first of all, the constant multiple rule to factor out the 5 and the 4 from these two arguments. And then now with these antiderivatives seen here, and maybe I should factor this one out. Let's leave behind 1 and factor this out to 2. And note that that is actually going to be x raised to the 0 power. Right? We can come along and say, well, from our power rules, how did I get that in there? Let me take that out. This is equivalent to this result seen here. Using the power rule, this power of x squared is going to bump up to 1 by 1 to 3, and we're going to divide by that new power of 3. And this x to the, we'll point out, first power is going to bump up by 1 to 2, and we're going to divide by that new power of 2. Right? And this third one, right, is going to bump up to the power of 1, and we're going to divide by the value of 1. Right? Using a little bit of our power rules to calculate each of these antiderivatives. Right? Now, this 5 will distribute across these two terms, the 4 will distribute across those, and the negative 2 will distribute across those, yielding these results, where these constant terms are just that. They're like terms that are some arbitrary constant. Where when we sum those up, here in this case, because I didn't denote them with any subscript, we'll just say they're equal to 8c. Right? 8 times a constant, where 8 times a constant is, again, just another constant. Where we can conclude in the end the antiderivative of our function, the polynomial 5x squared plus 4x minus 2 must just be equal to 5/3 x cubed plus 2x squared minus 2x plus some constant c. C being, again, any arbitrary constant. Where I was able to obtain that antiderivative by applying the rules, those 3 fundamental rules, as seen above. Sum and difference rule here, constant multiple rule here, which set me up for applying the power rule to obtain this rule here. Simplifying produces this result, which produces this result, where that constant in the end is nothing more than just another arbitrary constant. So in the end, we can say that the antiderivative is given by this function seen here. 5/3 x cubed plus 2x squared minus 2x. Where notice, we should probably say, right, if I took the derivative with respect to x for that quantity seen right here, right, that does equal 5x squared plus 4x minus 2. Right? The argument of our antiderivative. Right? That's what makes this the antiderivative of the function 5x squared plus 4x minus 2. Now, we were able to apply this derivative operator to this polynomial pretty quickly. We've developed the skills to say, well, yeah, this power is going to decrease by 1 and cancel with this 3. So that leaves us with 5x squared. This 2 is going to multiply by this constant multiple of 2, making 4 and decrease by 1. And this power of 1 is going to multiply by this negative 2, and that power of x is going to decrease by 1 to 0. X to the 0 power is equivalent to 1. Right? Where we've become pretty quick at applying the derivative operator to polynomials, you want to develop the same skills for finding the antiderivative. All right. If we consider applying that in a relatively quick manner to another function, polynomial, we might say here we have 3x to the 4th minus 1/3 x squared plus 4. Well, if we find the antiderivative of that, we could apply those 3 rules from above rather quickly. Right? Noting that that antiderivative operator would just distribute itself across the sum and the difference, being left with these these 3 antiderivative operations. We know the antiderivative of 3x to the 4th yields 3x to the 5th. The antiderivative of 1/3 x squared is going to yield 1/9 x cubed, and the antiderivative of 4 with respect to x is going to yield the value of 4x. We should be able to apply the antiderivative operator in a very similar manner, in a quicker manner, in 1 or 2 steps, like we had done for the derivative operator. All right? And we see that being done here. All right? where I could have been just as quick to draw my end conclusion seen here. Maybe we'll leave that in there as such. All right. So in this case, it was distributed across the sums and differences, as we had seen. Right? Those constant multiples were factored out, and the power rule was applied in each of these terms. Right? And once simplifying all those arbitrary constants, we end up with this statement in the end. Where if I take the derivative of these first three terms, it does yield me the argument 3x to the fourth minus 1/3 x squared plus the value of 4. All right? These first four rules, first three theorems, which 4 if you include the rule for the constant here, power rule for the constant, can be used to find the antiderivative for any polynomial function. Very similarly to how we had done it for derivatives. All right. Take a quick break here. All right, folks. I just have I shouldn't say a few more rules to give you here, a few more ideas, a few more, like I said, rules of antiderivatives. We have 11 more to kind of present here. They are all presented in a single theorem. They all come with their support in hand. So there's not much to prove. And where they do develop from is that understanding that to be an antiderivative of a function, you are related to the argument of your function. You are related to the function that you're the antiderivative of by taking your derivative, right? For y equals f of x, letting y prime be equal to f prime of x, what we're going to see in these relationships is that if I apply the antiderivative to f prime of x, these two operations cancel, and they're going to leave me with f of x. Right? These operations, this relationship is what's going to kind of be fundamental in the following theorems. And similarly, if we think about f prime of x being dy dx, we can see how this kind of plays out. This is equivalent to what would be the antiderivative of dy dx. The dx's would cancel, leaving you with the antiderivative of dy, right? They're the antiderivative of 1 with respect to y, which we know from the constant rule above is just equivalent to y plus c. Y being the function f of x, right? When we apply this antiderivative operator to a derivative, the result will always be a function whose derivative was the argument of the antiderivative operator, right? So these ideas are used in our support for the following rules. Here's the first rule. This should look familiar, and support should be easily accepted. And that is that the antiderivative of e to the x dx equals, e to the x plus c. And the reason for that is if I take the antiderivative of this, if I take the derivative of e to the x, the result here, its derivative is e to the x, the antiderivative's argument. Right? That's what these rules above are saying in general for our understanding of the antiderivative operator. That's how we're supporting each of these antiderivative rules. All right? If we look at another, the second, we have the antiderivative for the statement 1 over x. Now, what you'll notice is the antiderivative for 1 over x is the case for the power of x raised to the negative first power. And as we had noted, we cannot apply the power rule here is because x cannot equal the value. Well, our power can't be negative 1. Power rule being applied there would result in the antiderivative having a denominator of 0, which it couldn't have. It would be undefined. But remember, how we handle the antiderivative of x raised to the negative first power is that it is equal to the ln of x, or specifically we can say the ln of the absolute value of x. And we can say it's equal to the ln of the absolute value of x plus c, since if I take the derivative for the ln of the absolute value of x, which why the absolute value is because it simply gives us a domain of x not being allowed to be 0 and not strictly greater than 0. We can now dip to the negative side. When we think about 1 over x does describe values of the slopes of the lines tangent to the ln of the absolute value of x on either side of x for both negative and positive values for x. So since the derivative for the ln of the absolute value of x equals 1 over x, we can say the antiderivative for 1 over x is equal to the ln of x plus c. Right? We have this very specific derivative rule. Right? That absolute value of x makes little difference until you start to think about the domain of x. This result works for just simply x not equal to 0, whereas if I neglected using the absolute value in this statement, this would only be true for x greater than 0. Right? What this result allows us to do is allow this to be true for x's that are any value except 0. All right, take note. Third rules for the derivative, or the antiderivative of the sine x. The antiderivative of sine x is actually opposite cosine x. And the reason for that is because the derivative for the opposite of the cosine x is actually equal to what we might note as the opposite of the derivative for the cosine x. Right? Which, let's take this just another step further, is equal to the opposite of the sine x, which in the end yields the sine of x. All right. Let's leave this step out because we are running that a little long. So in the end, we end up saying, actually, we'll leave them both out. That's why I say in the end, this is the derivative with respect to x for the negative cosine of x can be said to be equal to the sine of x. Because of this derivative result, we can say the antiderivative of sine x is the opposite of the cosine x plus some constant c. Similarly, in our fourth result, the antiderivative of the cosine x is simply the sine x. And that's because the derivative of sine x is simply cosine. Right? Because the derivative with respect to x for sine x is simply cosine x, that does mean that the antiderivative for cosine of x, right, will be the sine of x plus c. Right? Quick derivative result. Now, what you will notice is these derivative rules or antiderivative rules are only for these specific cases of functions. And that's because they develop from these very specific cases for derivatives. All right. If we continue here, we're 4 in, so we have, 7 more to go. We do have some derivative rules for secant squared and cosecant squared. Go ahead and bring the cosecant squared into view too. Again, these are very similar. These develop from our derivative rules for tangent and negative cotangent of x, or cotangent of x. Derivative of cotangent of x is opposite cosecant squared, so the derivative of opposite cotangent of x would be cosecant squared. So that lets us able to say the antiderivative of cosecant squared x is opposite cotangent of x. And similarly, the antiderivative of secant squared x equals tangent of x because the derivative of tangent of x is equal to secant squared x. Right? We have these two derivative rules that are antiderivative rules that are very specific to these functions, secant squared x and cosecant squared x. We don't have antiderivative rules developed yet for just secant or just cosecant. And in fact, those rules I don't think develop until we talk a little bit about some Calculus 2 techniques. So you aren't going to see those develop until Calc 2. All right. So that's 2 more rules. We're 6 in, so we got 5 more to go. Also keep in mind there were derivative rules for secant and cosecant, where because the derivative with respect to x for secant of x is tangent of x times secant of x, we can say the antiderivative for tangent of x times secant of x is equal to secant of x plus c. And because the derivative of cosecant of x was opposite cotangent cosecant, we can then say the derivative of opposite cosecant must be equal to cotangent cosecant, which allows us to say that the antiderivative of cotangent cosecant must be equal to the opposite of the cosecant of x. Right? Plus c, c being any arbitrary constant. Right. So that was 2 more. That takes us up to 8. We have 3 more to look at here. And where the last 3 come in is if you remember your derivative rules for the inverse trig functions, sine, tangent inverse, and the last one, secant inverse. Where since the derivative for the secant or sine inverse was 1 over the square root of 1 minus x squared, we can say that the antiderivative of 1 over the square root of 1 minus x squared must be equal to the sine inverse of x, plus some arbitrary constant c. And similarly, since the derivative of the tangent inverse was equivalent to 1 over x squared plus 1, the antiderivative of 1 over x squared plus 1 must be equal to the tangent inverse of x plus some arbitrary constant c. And then lastly, we had the derivative rule for secant inverse gave us 1 over the quantity x times the square root of x plus squared minus 1. So if we take the antiderivative of 1 over the quantity x times the square root of x squared minus 1, that must be equal to the secant inverse of the absolute value of x. Right? All from those derivative rules for the inverse trig functions, sine inverse, tangent inverse, and secant inverse. Now you might be sitting there going, well, what about the cosine inverse? Didn't the cosine inverse have a derivative rule given by the negative 1 over the square root of 1 minus x squared? And I'll say yes, which does mean that if you took the antiderivative of negative 1 over the square root of 1 minus x squared, that would equal the cosine inverse of x plus c, but we don't go that far because if we think about negative 1 here, it can also be handled being brought out in front as a constant multiple of the opposite of that antiderivative, which would actually lead us to the opposite of the sine inverse in our result. And you're going, well, how's the opposite of the sine inverse equivalent to the cosine inverse? And I will say it is when you're considering that what we're exploring is the derivative behaviors that would describe the slope of the lines tangent to the curve. The slope of the line tangent to the opposite of the sine inverse of x is very similar to the cosine inverse's slopes of the lines tangent to its curve. All right? And that same trick can be used here in the case for tangent inverse and in the case for secant inverse. Right? The opposite of their behaviors describe the exact same slopes that would be described by the derivative operations on the cosecant inverse or the cotangent inverse functions. Right? So we don't have to consider those cases when including those into our fundamental rule list. And we can keep our rule list shorter by 3 statements, right? By just accounting for those as being constant multiples of with the value -1. Right? Now you'll again notice these are very specific derivative operation or antiderivative operations developing from these very specific derivative rules. Let me change this back before I forget. That has to go back to sign. And we have to change this back to positive. So let's make sure we do that. And all the others are the same. Okay. All right. These are very specific rules. This antiderivative rule only works for 1 over x squared plus 1. This derivative rule works only for 1 over the square root of 1 minus x squared. This derivative rule, antiderivative rule, only works for 1 over x times the square root of x squared minus 1. Right? They only work for these very specific forms for the arguments of these antiderivative statements. Right? If that was a 2 there, we'd have to be a little cautious. Or if that was an x up here, we would have to be very cautious. Other techniques would have to be applied. And those other techniques actually develop in calculus too. All right, keep that all in mind. Consider finding the antiderivative of the following here, folks, applying using these rules. Well, if we think about the antiderivative of 4 times the cosine of x minus 3 times the sine x, well, the antiderivative for 4 cosine x minus 3 sine x dx must be equal to 2. And if we distribute that antiderivative operator across this difference, and then treat the 4 and the 3 as constant multiples, we'll be left with the antiderivative for the cosine x, which we know is just the sine x, minus 3 times the antiderivative for the sine x, which we know is opposite cosine. Now, opposite cosine x combined with this minus 3 will simplify back to positive 3. So we end up with the antiderivative result 4 sine x plus 3 cosine x plus c, using the rules above. And I probably should put that one set in there. Let's say that this way. Let me put one more step in there. Not there. Let's put it right here. Let's highlight here, we still have the minus, and what this is turning into from the rule is the opposite cosine x. But when you multiply those together, you get positive 3 cosine x plus c, so that's where the plus 3 is coming from. All right, take note. Or here's one other case. All right, so I gave us that result. Consider finding the antiderivative. No, I give a couple other cases here. The antiderivative of 5 over x minus 3 to the e to the x. Well, that antiderivative operator will distribute across that difference. That 5 in the numerator will become a constant multiple and can be factored out in front, and so will the 3. Right? So really we'll be left with the antiderivative of 1 over x, which we know is ln of x from the rules above, ln of the absolute value of x. So this first term will turn into 5 times the ln of the absolute value of x. And we know from the rules above that the antiderivative of e to the x is e to the x. So this will be negative 3 times e to the x. Right? So that's where we get this negative 3 times e to the x. Where when we combine those two results, it becomes 5 times the ln of the absolute value of x minus 3 to e to the x plus some arbitrary constant value of c. Notice we don't really consider that arbitrary constant value until the end. As we evaluate these antiderivatives individually, right, the constant multiple could be considered in each of their individual cases, but in the end, they're all going to add up being like terms as an arbitrary constant multiple to become just one more arbitrary constant multiple. So it can be ignored till the very end of the calculation. And you see me doing that in these results. You don't need to algebraically track those values of c through the calculation. And I think I say that above in one of the examples of the polynomial. Here's one last case. Consider the function 1 over the quantity 3x squared plus 3. Well, the antiderivative of that argument, we might notice 1/3 is a constant multiple of that argument. We can factor a 3 out of the denominator as a 1/3. That 1/3 can then be factored out of the antiderivative argument, where we know the antiderivative of 1 over x squared plus 1 from the rules above very specifically yields the tangent inverse of our function, or the tangent inverse function. So this becomes 1/3 times the tangent inverse of x plus c. All right, that is applying, again, the 12th rule on, or there's only 11, so the 10th rule on that list above. All right, along with constant multiple rule for antiderivatives. And I think I say that result in the end here. All right, and that is, I believe, the end of the notes here. Let me just go ahead and finish that with those few examples, folks. All right, I'll give you 3 examples here of using the a couple examples of these 11 different theorem results given in this last theorem here, mixed with some sum and difference and constant multiple rule given above, right, for the case of finding the antiderivatives of polynomials. All right, again, notice these results are very specific to these cases. Right, they have to be applied in these very specific situations. All right, there is one more advanced rule we're going to learn this semester. It's a few sections away. It actually appears at the end of our next topic. So we really don't learn it till the very end of our study of calculus here. But it's going to be known as variable substitution or use substitution for antiderivatives. It's going to help us find derivatives for composite situations. Very similar to chain rule, right? But I believe it develops, you might relate to it a little bit with chain rule. You might relate to it a little bit with product rule. We'll talk more about it when it comes about. All right? But yeah, here we have these fundamental rules, and this is what we have to actually get us quite a bit of ways into Calculus 2, folks. All right? Our whole next chapter, as we go further into the study of antiderivatives, this is going to happen in the next chapter of study, where we're going to talk about integration. And what we're going to see is the topic of integration is another way to talk about antidifferentiation. It's 2 words are kind of synonymous with each other. All right, and we're going to see how this antiderivative operation here is going to be useful in calculating what we're going to refer to as definite integrals, or just integrals in general, and how it's going to help us find what's going to be called net area. These rules that we've learned for antiderivatives are going to be really useful for calculating complex areas. Areas that are bounded by functions, right? By curves in space. And finding those areas exactly. Right? That's kind of where we're heading here, folks. That is where we're heading here, folks. So, that antiderivative operation is going to be really helpful with that. And we're going to be using these rules all throughout the end of our semester here, finishing up our study of these Calc 1 topics. All right. So with that said, I'm at a little over an hour. This is a long video, so I'm going to end this topic here, and I will be back starting to look at integration. That is where we are heading, folks. So I will see you in that next video.